So far, I can see there are some people here in the UK. There are people also, lots of people in the US, New Hampshire, Colorado. We have people from the Netherlands, from Germany. So we can see this is a very international online session today. And this is the way that we like it, because at the end of the day, these issues that we are discussing today are very international and they're not geographically limited to one country or one area. So keep introducing yourselves by the chat. We love seeing you guys and what you're saying and where you're joining from. Usually we have people from everywhere, so it's always welcome. So today we're here to discuss how to make variable renewable energy projects with energy storage work. As you know, dispatchability, the ability to be able to use the energy or to dispatch the energy to the grid whenever it's needed instead of when it's produced, is one of like the milestones that renewable energy needs to reach in order to become for more and more renewable to be added to the grid. And this is what we're discussing here today. It appears there are people who have been studying this topic for a while and that have solutions for it now with technology that is well proven and that is competitive today. And I'm going to let them actually talk and tell you how they're making it happen. So first I'd like to ask Adrienne, please can you briefly introduce yourself? Tell us something about you and what you're doing.
Yeah, sure. Hello, everyone. My name's Adrienne Little, coming from Malta Inc., which is a small startup working in energy storage. Currently joining you from Sweden, but we are based in Boston, so I'm a bit of a transplant at the moment.
From Sweden, that's good. So as you can see, guys, I am based in Madrid. As you know, Adinsights' main office is in Madrid. We have Adrienne in Sweden. And what about you, Sigwen? Where are you based at the moment? Where are you based at the moment? Can you hear me?
Oh, hi. Sorry.
Hi,
yeah, hi everyone. Yeah, this is Xubin Ma, joining from National Renewable Energy Laboratory in Colorado, US. I worked in National Renewable Energy Laboratory for about 10 years as a senior engineer here.
So,
thanks.
What are you going to be telling us today? Just very briefly.
Oh yeah, today I'll introduce some energy storage for grid application, including some new projects conducted at NREL.
Excellent. So let's go ahead with it. I can see there are some old friends already online. So it's nice to see you, Eric. Thank you very much for supporting us and coming to our webinars. And there are many more people there I can see, and your numbers still going up. So Adrienne, can you prepare your screen and give us your introduction, your presentation? And whilst Adrienne is preparing herself, right? She's putting up her session, etc. Just to let you know, we are recording this, okay? We are, so don't worry. You can watch it again. You can send it to your colleagues. We do have the materials and we will be sending them to you in a couple of days, okay? You can send questions using the Q&A box at the bottom. Send them through and we will read as many as possible. Adrienne is going to speak, then Sigwen is going to speak, and then we will take the questions. So without further ado, Adrienne, the floor is yours.
Great. Thank you, Belen. So the subject of this webinar is how to design and build cost-competitive thermal storage, and specifically in what I like to call the age of storage. And what I mean by that is we're specifically entering into a new time where we need to think fundamentally differently about how we're designing and bringing thermal energy systems to market. And what I mean by this is, previously looking at a lot of thermal systems from kind of the steady state standpoint, base load, constant usage with time. But now we're getting into this case where these thermal systems, including the storage systems, are going to have to match the variable loads on the grid. And there's many interesting technologies, especially in the thermal space, that have the ability to be cost effective and competitive here. And so I'll be talking to you about specifically a potential option that Malta Inc. is working on. First, giving you some background of the company, going a little bit into the technology, and then how we see the markets for thermal storage developing. So to give you a little bit of background on generally the utility of storage, probably familiar to many of you on the webinar here. Really, we're looking at solving this issue where demand does not meet the generation load. And if you look at this graph on the right here, we're looking at load as the red line and what's available as all the other colors. And so essentially we're trying to shift load from one time to another, load shifting. And so we're in an interesting situation right now where if you look at typical renewable energy generators, let's say solar PV, let's say wind, the cost of that electricity is now getting to the point where it is below the cost of generating electricity in a carbon intensive way. And so the tipping point is where we can start fulfilling this equation at the bottom here, where the cost of renewable energy generation plus the cost of storage becomes less than the cost of generating carbon intensive energy. And once we hit that tipping point, which we believe is very close, not quite there yet, but getting very close, we're going to start to see a fundamental shift in how the grid is structured and how we use electricity, and a lot of things will start changing. So to give you some background, some, let's say, history on Malta Inc., the small startup company that I'm currently at, we have a concept that started back in 2012 and was developed in a previous life before it was adopted by X, formerly known as Google X. This is Alphabet's, the quote unquote moonshot factory. This is where they take on projects that are high risk, high reward, and develop them, test them, and try to get them to a point where they're ready to spin out and become full-fledged projects. So the concept spent about, let's say, 2 years there being tested, and it survived these tests. And then when we came to 2018, Malta spun out as its own independent company, independent of Alphabet, with BEV signed on as our lead investor. And I got a little tickle out of this article that came out from Quartz saying Bill Gates led VC is funding a storage solution that's a refrigerator on steroids, which we thought was kind of funny when that came out for all the thermodynamics and heat transfer nerds out there. In the next couple slides, I'll explain why this is a refrigerator on steroids. But now, so it's full speed ahead. We are looking fundamentally at developing a new product on a short timeline and bringing that to market. And so fundamentally, what is this technology doing? We take electricity from the grid, we store it, and then we release that electricity back onto the grid when it produces the most value to our customers. And so in between, we have this battery-like thing, but it's not a battery that's full of chemicals, like let's say your standard electrochemical battery or flow battery or whatever. And instead is full of things like heat exchangers, pipes, valves, turbo machinery. It looks very different from, let's say, your lithium-ion battery. So what exactly is in that battery? Well, we call it electrothermal energy storage, and fundamentally it's a heat pump, heat engine. So in our charge mode, we're operating as a heat pump. This is the refrigerator on steroids. This is where we take electricity from the grid, and from that we produce hot and cold. The heat we store in big tanks of molten salt. This is the same molten salt that you see used in CSP facilities worldwide, solar salt. And on the cold side, we have large tanks of an antifreeze-like solution where we store the cold essentially. And then later when we need that electricity back, we reverse the cycle and we run it in a heat engine mode. And a heat engine, this is typically, what you see used in power plants and things like that, using heat to spin a turbine and produce electricity. Very similar concept in discharge mode, a heat engine, using the heat from the hot tanks and the cold from the cold tanks to run it and get your electricity and put it back on the grid. So fundamentally, that's the concept. And when we're looking at the types of technologies we would use here, I already mentioned it on the hot side using solar salt, which we take from the concentrated solar power industry, as well as a lot of the other technology there, the heat trace, the pipes, the valves, the pumps, the things like that. On the cold side, pulling a lot of technology you see in the air separations industry, in the liquefied natural gas industry, where they're operating at temperatures in this region. And in the middle, we're looking at turbo machinery technology that is fairly common to the gas turbine industry. And so one thing we like to say here is that it's almost like we're putting together a puzzle and taking well-established technologies and putting them together into a new application in this growing market. And that growing market I'll get into a little bit more in a second. And so, you know, why do we believe that this is a competitive concept? Well, it comes down a lot to it being flexible in deployment, but also having competitive cost, both very important when considering a competitive energy storage technology. So in terms of cost, you know, targeting costs that can be half the cost of lithium-ion batteries, you know, now and in the future. And then also in terms of being able to use this in many locations, this is a energy storage technology that does not need caves like compressed air energy storage. It doesn't need mountains like pumped hydro energy storage. This is something that could be placed in any physical location that makes the most sense to the customer. So for example, a sensitive node in the grid, or maybe a diesel generator replacement, or, you know, I'll get into some more applications later. And another feature of the system, and what really helps with cost, is the fact that in the Malta system, you have the power of the system and then the duration of the system. And one analogy we like to use here, it's like buying a car. When you buy a car, you buy an engine with a power, with a gas tank, which is the duration, how long you can drive that car for. In the case of a lithium-ion battery, whenever you buy a new battery pack, you buy a little engine and a little gas tank. And that's fairly expensive, buying a new engine and a new gas tank every time. So the cost of your system goes up pretty quickly with duration, as you can see with this orange curve here. But in the case of a Malta system, what you can do is you buy the engine, but then you can change what you choose to purchase for the gas tank. And so what this means is that, especially at the longer durations, more than, you know, let's say around 6 hours, we can get competitive costs, because the incremental increase of, let's say, the cost of a larger salt tank is fairly small in comparison to the cost of an additional battery pack. And so this is where this solution, Malta solution, but also other solutions like flow batteries with a similar concept, the decoupling of the engine and the gas tank, start to make a lot more sense at these longer durations. And so, you know, considering all of this, we really see Malta as an implementation challenge, as I said, bringing together all of these fairly well-established technologies. And we don't see it as a basic research challenge. We're not coming up with any fundamentally new chemistries, new materials. We're really using, in our eyes, what is already out there in terms of technology. And so what do we plan to do next? Well, next step, our goal, is to build a pilot plant, a 10 megawatt pilot plant. And it is this scale at which we see our small scale product. We also see our small scale product being 10 megawatts. So in the course of building a pilot plant, we also see ourselves as developing our first product. Now, this product is better suited for certain applications, whereas in the future, the plan is to develop a nominal 100 megawatt product, which is different or good for different applications. So at the 10 megawatt scale, looking at things like island grids, critical backup for places like data centers, deferral of transmission and distribution build out, firming renewable power and microgrids. At the larger scale, really looking at whole-scale energy markets, vertically integrated utilities, reaching storage mandates and incentives, which are becoming quite challenging in the coming years. And then, of course, also firming renewable power. The one way I like to think about this is we're really targeting a technology that can, in a sense, be the Swiss Army knife of energy storage technologies for long durations. You know, a technology that's really not dependent on anything geographic or site related. And so if we look at this from a technology white space standpoint, this is a nice graph from the US Department of Energy, where they're looking at all the different battery chemistry and technologies, also the larger scale options like pumped hydro and compressed air energy storage. And you can see that Malta is really in this space that's in the upper right-hand corner here of large size, large power, and many hours. So we're looking at really big installations. This is not something that goes in the back of your house or anything like that. But the white space we're really playing in is where pumped hydro is doing well and compressed air energy storage is. So one way of thinking about Malta, it's kind of like pumped hydro, but without the hydro, because it's playing in that same space, but we just don't have the geographic constraints of the mountains, of course. Okay, so that's kind of how the technology works and how we think about cost. What does the market look like for storage upcoming? So we did a comparison of these different studies looking at what we predict to be installed in terms of energy storage in the coming years. And generally you can see there's a lot of spread between different predictions, but even the lowest ones are predicting hundreds of gigawatts will be installed worldwide. And specifically, if you look at the one that's circled there, the Bloomberg New Energy Finance, predicting 700 gigawatts of capacity installed by 2040. Well, they just came out with a new study. Now they're saying 950 gigawatts by 2040, and we have this nice breakdown of what countries they predict this installations to be in. And so, this generally seems to be a trend that with every year, as they start predicting the storage markets, they keep under predicting. Like, oh wait, no, we think it's more. Oh, maybe now it's a little more, maybe more now. So, I mean, this seems to be a trend, but generally there seems to be a lot of stuff that has to be installed fairly soon from an energy storage standpoint. And so how are we targeting, or how are we thinking about bringing this storage product to market? Well, the philosophy is targeting what we call an MVP, a minimum viable product. So really, we don't want to get it perfectly right the first time because we're really concerned about time to market. And yeah, time to market is something we can get out there to show people that this works. And then with time, with serial number 2, 3, 4, etc., we can start refining and getting to perfect efficiency targets and things like that, and adding features like waste heat utilization that different customers might find interesting. And so, this is the challenge we see on the in industry, trying to choose how to do this product development so that you have something of value at all steps in the process, instead of waiting a very long time before you have something that anyone's willing to purchase. And so there's many options for energy storage usage, and I think I'm running out of time here a little bit. So I'll go over this very quickly, but there's many uses for storage. This is a US-based thing.
You're okay, don't worry, Adrian, you're okay.
Yeah, okay, all right. So each line here is a different use case for energy storage, but I mean, I suppose you could read through this if you want, but the point to make is there are many value streams for storage. There are many things it can be used for. And previously, at least the way policies were sent up and the way people were thinking about it, storage was only being considered for certain use cases. And now those use cases are expanding. And I think one of the more interesting ones here is the lower line, transmission, thermal, and voltage violations. Now what's happening is, as we add more, let's say, wind turbines and solar PV to the grid, we're losing the ability to have inertia on the grid, which is actually quite important. We need spinning things on the grid to maintain voltage requirements on the grid. And so this is something that a system like Malta can provide because it has spinning things on it. And so more and more of these opportunities are coming to light as we start talking to different customers, and we hear about different pain points that are suddenly coming up on the grid. And one of these pain points is transmission violations. And what we're seeing is, as the distribution of generators changes, so does energy flow in the grid. And so this is resulting in a lot of change in load flows on the grid that are resulting in voltage violations and thermal violations. And we're also seeing cases where we may need more distribution installed. It may be challenging to do so because of land restrictions. And so, this is just kind of maybe a little bit of a niche of a energy storage application, but still kind of interesting, and this need may grow with time. And another interesting thing, related to Malta specifically, because it's fundamentally a thermal system that in many ways looks a lot like a gas turbine power plant with spinning machinery and pipes and valves and heat exchangers and things like that. We're seeing that the future of, we're seeing that a lot of, on the right here, old assets, so specifically coal power plants, and I use the example here of Europe, are being decommissioned, ramped down, shut off. And from a social standpoint, this is interesting, and it's a challenge for the people in these locations that have these really valuable skill sets of maintaining boilers, welders, these sorts of skill sets you would see for thermal power plants, and their core business is going away. And so there's many options here to install things that look like thermal systems, like Malta's, use existing assets there, but also using existing workforces there. And this is something that helps these types of technologies get ramped up, very quickly. And so, this is my last slide here. I kind of like to throw this out because if you haven't read these two books, I really recommend that you read them because they're very interesting stories about bringing technologies from concept to execution. Now, in the case of the atomic bomb, that wasn't the greatest example of execution, but the alchemy of air is talking about using fertilizer to grow crops and feed the world. But one thing I want to point out here is in these stories, it's really about the importance of not just inventing a technology, but establishing an ecosystem. And by that ecosystem, I mean establishing a manufacturing base, establishing a base of EPCs that can build what you're trying to do. Operation and maintenance, supply chains and protocols. In a sense, it takes a village to raise a technology. So you have to think outside of just the technology if you're bringing something to market. And then, of course, it's very much a staged process. You see stage development in terms of the minimum viable product, funding sources, and even teaming. So it requires a lot of flexibility as you go through this journey. And so with that, I'll leave it there. Thank you.
Thank you very much, Adrienne. I'm going to ask you to stop sharing your screen. The alchemy of air. Excellent. I'll write that to my reading list. You have a bunch of questions. You can start if you like to answer them by text, and then we can do a catch-up later. Sigurd, go ahead. Can you please share your screen and begin your presentation? And whilst Sigurd gets ready, just a reminder, we are recording. You will definitely get these presentations. And I'd like to say also hi to the many, many friends that seem to be present here today. I've seen a number of you already that knows us really well, and I'm really proud that you guys keep coming back. And thank you very much for your support. We also, oh, you're ready now. Excellent.
Thanks, Belen.
So that is,
can you hear me well?
Yeah, we can, but it seems like, I don't know if it's just me, but I can see your presentation is a little bit zoomed in somehow.
Oh, okay. Perhaps
I only see half of the logo. I don't know if everybody sees the same. I think so. Can you retry, okay. Stop sharing the screen and share it again and see if it works?
Yes, perhaps because I have a high resolution display. So
God knows. Technology, right?
Yeah, but if just cut up to the logo, that's probably be okay.
Just try for me, because we get a lot of things cut off. So try for me, like stop sharing the screen and share it again. Some people over here are saying, yes, can't see full screen. So can you go down here to the button? Yeah, that one there. Let's see what happens. Yep, it should go into full screen now, but it would be a shame if we don't get to see the PowerPoint. It's okay, we will get it to you anyhow, but okay, now, if you go to display settings for me, yeah, click on it, please. And no, neither of those. Again, we cannot see it properly, but okay, go ahead and see, let's see how far we get. And don't worry, guys, we will send this to you.
Okay, thanks, Leanne. Thanks, Andrew, for the first presentation. I'm Xibin Ma, sitting in National Renewable Energy Laboratory. I'm right now in this building, and to talk about cost-effective thermal energy storage to support variable variable renewable power generation. So I first talk a little bit about energy storage background, and then introduce NREL's Enduring project for long duration energy storage that's using thermal energy storage, and also discuss a few projects at NREL to develop CSP technology with energy storage. So with Andrew's introduction, I'll make it here simple. Basically, current development is more focused on battery type of storage, but on the other side, with the renewable integration into the grid, and many states have set up their carbon-free energy goal in the middle of the century, and the challenge to the grid is more and more because more renewable integrate and more baseload fossil and nuclear plant will retire. That imposes the great uncertainty for the grid, and to overcome that, massive storage would be needed. And at this point, most of storage technology deployed is pump storage hydro in the bulk storage side, and compressed air has been discussed a lot. But thermal energy storage has great potential, but is underrepresented despite many CSP plants have incorporated thermal energy storage that effectively shifts the production to the evening and the peak hour. And from this graph, we see that for the long duration bulk storage, the key is to have cheap storage media, such as water or air, which are essentially free. And thermal energy storage also keep these advantage that use low storage cost media. So thermal energy storage has broad applications, and the application on the power generation has many types, and the development mainly focus on sensible heat storage, such as molten salt has been deployed with the concentrated solar power plant. And more attention has been aroused on using solid media as storage material because it is inexpensive, it's abundant, and can be obtained from the nature and compatible with the environment. So here we basically talk about NREL project use solid media for long duration energy storage purpose. So the purpose of this project is develop long duration electricity storage by using low cost thermal energy storage and high efficiency thermal power cycle. So this is a project awarded by DOE Upper E in this program to develop and demonstrate a component cost and performance for the next step technology to market purpose. And the Enduring long duration energy storage system, the aims at store the energy for several days of power supply in the long run. In the short term, also can do price upcharge and the generation shifting, so that to enable large amount of renewable integration into the grid to support the grid security and the resilience. This is a project team that's including national lab, industry, and academics. So the way the Enduring system works is like a thermal battery, but in a larger scale. So essentially, at the low-cost electricity off-peak hour, the electricity from grid will heat up the particles by electric heater to a very high temperature, and the high temperature particle will store in an internal insulated silo, and for a certain period of hours, and then discharge at the peak demand hours into a fluidized bed heat exchanger and heat up the gas coming from the compressor of the gas turbine, and then the heated high pressure gas drives the turbine and the generator to generate electricity back to the grid. The feature of the endurance system is aiming at longer storage hours from 10 to 100 hours, and in power capacity of 60 to 300 megawatts also can be scalable. And this range of the power is well compatible with general electricity gas turbine combined cycle. So we have GE in our GE Global Research in our team to look into the modification of the power cycle system. To increase the cycle efficiency, we essentially try to obtain the high temperature particle, about 1,000 degrees C, to store for get the adequate gas turbine inlet temperature. And in this project, we'll develop a novel fluidized bed heat exchanger with gas particle direct contact, so that gas can obtain the maximum temperature from the particle, minimize any irreversible losses there. And we also can leverage the assets from retired thermal power plants, such as substation, generator, gas steam turbine, or heat recovery steam generator to lower the capital investment. This system has siting flexibility without any geographic restrictions. So that's an excellent complementary to pump storage hydro, or contrast to compressed air energy storage that they need specific geological conditions. So as mentioned earlier, the key for large-scale bulk energy storage is to have cheap storage media. So in our case, we use silica sand or sintered bauxite. Those are mined from the nature, from the mines, and need little processing, so the cost is pretty low. For instance, silica sand is a few $10s per ton. To the bauxite is a few $100s per ton. That is excellent economic compared with molten salt that current case is like $25 per kilowatt hour. So our storage in the range of $1 to $2 per kilowatt hour is about 1/10 of molten salt for several reasons. First, we have a larger temperature difference by running a combined cycle, create a larger temperature difference from the cold and a hot side, so that have high energy density. Secondly, our material is cheaper than salt. Thirdly, we store both the hot and cold particles in the same silo, same containment, because the solid particle can be easily layered of the hot layer versus cold layer. So they co-located in one containment. That also cuts cost by half from what 210 molten salt does. Although salt wouldn't be able to apply to this case because our very high temperature. Another key parameter for energy storage is on the round-trip efficiency. So basically, battery claims has a pretty high efficiency, but battery efficiency varies. The reason is that the higher the current is drawn, the more irreversible losses in the internal resistance and polarization will occur that lower the battery efficiency at very high power discharging. So it's a range. And people also study a lot on the compressed air energy storage and claim 60% efficiency. My study found is that if without heat recovery from compressed air and dissipate that heat and later on need the natural gas to reheat the gas back to the turbine, that 6% a lot is coming from the fuel heat. So electric to electric efficiency is very high, but the energy efficiency is not significantly high. So what thermal energy storage can do is it does have ability to increase the performance efficiency. For instance, in this case, we look into gas turbine inlet temperature that in our range about 1100 degrees C, and we can get about 53–54% efficiency and then subtracting the per-circuit loss, it still can get 50% round-trip efficiency. So other attractive technology that that understudied recent years, also moving to high storage efficiencies, such as pumped thermal energy storage, as Engine introduced. So with those performance and the cost assessments, so we estimated our cycle cost is around, a storage cycle cost is around 5 cents per kilowatt hour at 2.5 cents kilowatt hour electric charging price, which is following the upper E levelized cost of storage calculation formula. So based on round-trip efficiency of 50% and power system cost of 600 to 700, that is basically based on IEA's information on the current gas turbine combined cycle. But of course, those new built gas turbine combined cycle plant is fairly in the larger scale, and this will be challenged for 300 megawatt to reach that price. But if we leverage retired power plants with those infrastructure and some components, we still can achieve that power system cost. And with less than $2 per kilowatt hour particle storage cost, we're fairly confident that we can achieve our target even for most challenge case of 100-hour long duration storage. And the difference from long duration storage versus like 10-hour storage is that the cycles less per year, so therefore there's less chances to recover the profit and earn the revenue through less cycles. So therefore, it's more sensitive to the capital cost of the power system and the storage system. But for low storage hours, it's fairly less sensitive because it will cycle more. So we see our path would have start from current need in upcharge, and with technology development and the economic need more longer storage time to move to longer storage application. And this is also illustrate what Engine shows, that the decoupling of the power from duration, that the thermal energy storage can do well in that perspective. Next, I'll introduce a few projects at NREL, mainly on the Gen 3 CSP side with new generation of energy storage, including molten salt pathway, gas phase pathway, and some development on the pumped thermal energy storage technology. So the Gen 3 liquid phase pathway is looking into molten chloride salt to reach the solar heating temperature so that it can drive a high efficiency supercritical CO2 power cycle at 700 degrees C. So the salt temperature is set at 720 degrees C. So this is the loop of the liquid system, and these projects divided into 3 phases. Phase 1 and 2 is on the material development and the pilot design, and phase 3 will be demonstrate a pilot system in Sandia solar test facility at the 2 megawatt thermal level. And this is the liquid phase team that including national labs and international partners. Also have industry and other organizations involved in these large projects. And another path on the Gen 3 development is looking to gas receiver that heat up the particle at the storage medium in the on time, and then the particle will heat up the working fluid of supercritical CO2 to drive the high efficiency power cycle to achieve a lower levelized cost of energy. So this project also divided into 3 phases, and phase 1, this first 2 years, we're looking reduce all the risks, and phase 3, we're looking into a pilot generation. The team of the gas phase is led by Britain Energy and involve various industry and universities. NREL is part of the team member. Another project at NREL is looking to develop pumped thermal energy storage and integrate with CSP power cycle. So this is take advantage that through the compressor and the turbine to get hot storage and cold storage separately, and in the discharging process, the power cycle can use the cold storage to improve the power cycle efficiency to get high efficiency as indicated earlier. So this is a team led by NREL and with 2 universities participate. Here's my presentation, and thanks for your attention. Welcome any questions.
Thank you very much, Singwen. I'm going to ask you to stop sharing your screen. It's still a mystery to me. You know, we organize tons and tons of this, and almost every time we have something new, you know, that we have to learn to react to, and we're really sorry that you haven't been able to see the full presentation, but hopefully because we sent you the link, you have been able to, and we'll look into how to sort out for next time. Okay, Adrienne, you were busy. You've replied some questions, so I would like to ask you first. You know, what have you seen in terms of the questions that you've been asked? You know, what do people want to know?
Yeah, so a few of them I think are better answered
live. I know, but so far, what have you been answering so that we are all up to date, and then we'll take it with the other questions.
Oh, what did I answer? I forgot. Someone was asking about temperatures and powers and
specific things,
like
right?
Okay. Yeah. So there was one question here. Why do you think the world has become so quickly obsessed with the potential of electrochemical batteries for grid scale storage when there's
that is a very good one, yes. Yeah. This is actually, I know who's behind this question. So what is your answer? What do you think? What is the obsession with lithium iron at the moment? Where is it coming from?
Yeah, well, so I mean, this is fundamentally a technology that's come out of other existing industries that use lithium-ion batteries. You know, one thing is, of course, electric vehicles. And so, you know, this was a natural, I would say, progression of the development of lithium-ion battery technology to grid scale. And so, you know, I think that's why it was certainly first to market, and now it's being adapted for different grid scale applications. And it's a great technology, and we're seeing a lot of very successful installations. Now, the way I like to look at it is a lithium-ion battery is more of a nimble energy storage option, in the sense that it can do things like frequency regulation, it can discharge very quickly, things like that. But when you start looking at duration, so if you're looking at a duration, number of hours of discharge, let's say getting anything longer than maybe 4 hours, you start seeing a big drop off in the installations at that duration. And that's because the cost per kilowatt hour is starting to get much higher. Also, there's, you know, some other issues with installations in terms of overheating and things like that. And so in terms of, you know, this is what I was trying to say back in one of my slides, is as you get to the longer durations, that ability to decouple that engine and that gas tank becomes very advantageous from a cost standpoint. So let me.
There is one question here that I'm dying to ask you, actually, Adrienne.
Yes. It
is very simple, and it says, is the Malta technology cheaper now than lithium iron?
Yeah, so of course I'm not at liberty to talk about our exact cost targets, but I will say that the goal here is to pull from technologies that have already been developed at a commercial scale. So as I mentioned, on the hot side, concentrated solar power; on the cold side, a lot of technologies from LNG and air separations, and in the middle, gas turbines. And so from a cost standpoint, we do have a decent idea of what these are going to cost. And also, Malta is very focused on setting up this ecosystem of equipment manufacturers and O&M contacts to make this technology. And recently we've partnered up with major OEMs on for all the different parts of our system. And from there, we can have a fairly good understanding of cost without actually building a system and running it yet.
Yes, but more or less than lithium ion. Okay, well, give me a time frame. Say 3 years time. Do you believe that in 3 years time you will, I'm going to assume that you are still be, because I mean, honestly, long term, the long duration lithium iron is not cheap. We know that. It's not competitive, otherwise we would be doing it. Mm-hmm. So in 3 years time, do you think you will have a cost advantage, a significant cost advantage over whatever lithium iron is going to be? Correct, yes. Yes. Mm-hmm. Singwin, I was wondering whether you have anything to add, since you guys are researching, and you're trying to get these systems to be competitive. What's your take on in terms of costs, and what can be achieved through a thermal system instead of lithium ion?
Yeah, as my second slide shows, that bulk energy storage for long duration situations really need large storage quantities, that the storage media requirement is huge, is massive. So in that case, it's better to have low cost material. The free air, free water, that's what case and pump storage does. And in our case, we use very rudimental elements like sand and minerals with little processing cost. And compared with lithium-ion battery, you have mining reserve. You also will compete with transportation, electrification of the transportation with electric vehicle will take a huge chunk of that, although lithium always can be recycled. But again, the demand is pretty high and the price is always be a challenge in terms of make as a massive storage media. And also from engine slide can see that decoupling the power and duration is a smart move towards larger scale storage, because this will represent in the future, because many states looking to 100% carbon-free energy in mid of the century. That means we need the storage to displace all the retired coal or nuclear plants, so that provides the baseload, reliable power supply. That means the market in the gigawatt size, and that's lithium-ion battery alone could not make up that. And we do need these kind of thermal power together with the larger storage capacity to support the grid.
So actually, I'd like to add something to that, kind of reinforcing it. In a sense, I think when we're looking at these longer duration technologies, especially the thermal ones, we should think about them as complementary to lithium-ion batteries. They're not really in direct competition because they serve different purposes. The lithium-ion batteries are good for the frequency control and the first couple of seconds, minutes. But for the thermal systems, with anything spinning, with anything that has to heat up, you're going to look at something that has a startup time that's more like a, let's say, a gas turbine peaker plant. So that's, let's say 5-10 minutes or more. And so, the real solution is going to be a combination of both systems to provide the full range of storage services on the grid.
Thank you very much.
That's an excellent point. Yeah.
Would you want to add anything else, Singwin? Don't worry, go ahead.
Oh, I mean, that's an excellent point, and also that's the purpose that I have that chart divided into two, it's actually 4 quadrants. So it has more for the power quality, distributed energy resource, for shorter discharge hours, that most advantage from battery or electrochemical devices like cell capacity. And on the other side, we'll have these long discharging hours, long duration that separates the power generation from the storage media, like hydrogen fuel cell, moving to thermal energy storage without geologic restriction, up to pump storage will still be a good storage technology.
Okay, there is a few more questions here that are very interesting. One concerns, okay, just to understand, there is no pilot, someone says here, is there any pilot of variable renewables with TES at the moment? And I understand there isn't, that the one that you're building, Sigwood, would be the first. Am I correct in this assumption? The first pilot will be yours? Can you hear me? Yeah, okay.
Ask Andrew, right?
Yeah, I just wanted to make sure, because I think so, but I just wanted to make sure. And there is a bunch of questions here regarding efficiencies. People seem to not believe the fact that, you know, if you take the electricity and then you use the heat and then you put it in the molten salt and then you run it through a turbine, they're like, oh, it seems like the efficiency is lost here. I would like you guys to answer to that or explain that directly. You want to start, Adriana? I can see you there, like, let me. Go.
Yeah. So it's a very good question, and there's multiple parts to that answer. So, you know, I think part of that question is, you know, why take electricity and convert it to heat? You know, as an engineer, that, you know, this sounds like a horrible idea. But you know, looking at the Malta system, for example, one way to think about efficiency is that it's, you know, the charge efficiency and the discharge efficiency. Now, there's some thermal energy storage systems out there that, for example, take a resistance heater and heat rocks or heat salt or something, and then they use that heat to run a steam turbine to produce electricity. Now, in that case, the efficiency of your system is 1, that's the electric resistance heater, nominally, times the efficiency of your steam power plant, which, you know, 30–40%, okay? Now, in the case of a Malta system, we get a little bit of a multiplier because we have the heat pump in charge. So the COP, the coefficient of performance of the refrigerator on steroids, higher than 1, multiplied by the efficiency of our discharge. So that is what it is. And then from that, we get this essentially a little bit of an efficiency boost because of that heat pump functionality. And we can do this because we have a lot of common, let's say, hardware between the charge and discharge system, so we get that multiplier of efficiency with minimal increase in system cost.
Do you want to add anything to this?
Yeah, on the efficient side, our approach would look into electric heater that's 100% efficiency. On the other side, we try to push up the thermal power cycle efficiency. A question asked, can we apply to steam power cycle? Certainly. Only thing is that probably need to go into supercritical steam cycle that get to 50% round trip efficiency. On the other side, we do have the potential to run gas turbine combined cycle so that we can get about 50% round trip efficiency. Of course, our technology also can, the particle storage also can support other type of power cycle, so that can support their efficiency target as well.
And I just want to throw out there that people should be asking about efficiency, yes, but also be asking about cost, which they are. But there's a balance between those two, of course, and that's going to change depending on the customer. And so especially we see with these long duration energy storage options, getting the max efficiency is not what customers want. Often they're looking at cost and, you know, where their electricity is coming from. So.
Yeah, good point. I think someone has also mentioned that point in the chat, so good that you bring it up. I also like to take this opportunity to say, if you guys are worried about the whole technology with molten salts, it's a very well-known technology. It's been going for years and years. We have it under control here in the CSP industry. And if you by any chance doubt, you can see, take a look at the DIWA project that has 15 hours of storage through the night. That's been built at the moment at record prices. So yes, this stuff is proven, it's bankable, and all the rest of it. And before we leave, the last question, since we're running out of time, is what is the potential of this technology to really phase out coal? I know we're looking at having a webinar about this particularly, because some of the countries are looking at recycling coal plants and using a system where they can withdraw electricity from renewables from the grid when it's not needed, store it and then use it later as thermal storage, and use it this asset that otherwise would have been, you know, essentially just thrown away. You know, you have to pay actually to take it down when you can use it for something else. But what is the actual potential? What do you see this as potential going forward for this technology? Who wants to start? Sigmund, do you want to start first, and then we can let Adrienne also give her point. Go for it.
Yeah, you know, if go carbon-free energy goal, then coal displacement is a scenario, and we're not competing in that scenario, but we are supporting the coal plant if they could reuse those thermal power generation integrate with thermal energy storage that actually can rejuvenate and repurpose the coal plant, so give them second life. And displaced coal, mined coal can go into produce chemical or more valuable materials. So I think our technology is facilitating this industry, and also from supplier chain side also can use those equipment, and the manufacturing can continue those aspects.
And the know-how. Yes, and Adrienne?
Yes, agreed. So it could be as basic as, you know, using an existing ultimate heat sink on site. It could be as simple as using existing foundations, things like that exist on a site. Or it could be, for example, using a coal boiler as, like, I think of it as like range anxiety. What if you can't charge your system fully? Can you instead charge it with the coal boiler if instead you don't have enough wind and solar on the grid? So I think there's, you know, a lot of different ways to integrate these thermal storage systems into existing coal plants. But, you know, I just see it as such a unique opportunity, unique to thermal stuff, thermal storage, where we can use the existing workforce there and give jobs to these people that have incredible competencies in many different technology areas, and give them essentially a role to play in this new energy transition.
Yes. Thank you very much to the two of you. I would like to also take this opportunity to thank our sponsor, SQM, which is a provider of molten salts. So I would take a look into this company, a very interesting company. Very well-known technology, as I was saying, and thank you very much, Sigmund, also for your expertise and sharing with us. Thank you very much, Adriana, for sharing with us and your expertise. And thank you very much to all of the audience for being here today. Variable renewables is a challenge, especially when we want to go towards 100% renewables over time. Let's not talk about 100% renewables, people get a little bit scared, but let's say 80%, you know, that sort of thing. We need to be starting to talk about variability. Dispatchability is an issue, is a challenge. And here is a ready-made solution with years and decades of bankability and technology know-how, and it's a proven technology. So it's one of the ways we can look at it. The question that we need to ask is this competitive? And the answer appears to be yes. So I'm crossing my fingers for this to become a fully fledged industry very soon. Thank you very much, you all, and I'll see you in the next webinar. Thank you. Bye.
Thank you. Bye-bye.